We left off talking about the SN2, and we talked about the rate. We talked about the transition state. We talked about the rate law. If I'm not mistaken. Let me make sure we did. Did we talk about the rate law? Yes. Yeah, we did. All right. So we talked about the rate law, the rate. We talked about the types of the types of substrates that work best. Primary and secondary can both do SN2. Tertiary cannot because it's too crowded for that mechanism to take place. All right. We also talked about the solvation of the nucleophile. So we have to use an aprotic solvent. And there's a list in this handout that has all the solvents and aprotic and protic and all that stuff in there. One of the other things about the SN2 is we talked about inversion of stereochemistry with a different example, but that backside attack of the nucleophile is a key characteristic of the SN2. That's why you always see inversion. So if you start out with your leaving group on a chiral center and it's R and the product, that new product, that chiral center is going to get inverted and become S and vice versa. All right, so let me pull up. Well, let's look at the examples here for SN2, and we'll talk about the E2, and then what I want to do between today and Monday is talk about all the mechanisms together, and then the rest of the time we spend in this unit, we'll spend just working through examples like practice problems. All right. So for the top example, I think we did this one already. So let's look at this example right here. And it is SN2 for several reasons, right? So you see the question asks predicted products. Sorry about that. Predicted products of the following reactions labeled nucleophile, a base, and leaving group. And we know it's SN2 because of these factors right here. So this molecule right here, is that a primary carbon where that iodine is?
Yes.
Primary carbon. So once you see that, it's a foregone conclusion that if it's a substitution and it's a primary carbon, it's going to do SN2. And so here's my substrate. We call this the substrate, or we can call it the electrophile. And this is my nucleophile, right? Dichloromethane is an aprotic solvent, right? So dichloromethane is aprotic. What's the product of this reaction?
Would you
go ahead? Come on.
Substitute the iodine for the
Substitute iodine, you say, for the methyl group?
Mhm.
Yes. All right. So this is a simple, again, substitution where your leaving group, which is iodine. Can somebody look on the list and tell me if that's a good or bad leaving group?
It's a good leaving group.
It's excellent. It's an excellent leaving group. So iodine is, and again, that particular feature of iodine is based on the fact that it has a large atomic radius, and if it's in a covalent bond with carbon, that bond is really long and it's easy to break. So this is my product for that, and let's just go through the exercise of writing the rate law. So rate equals K times the concentration of my substrate and my nucleophile. All right, that's always going to be the case for SN2. So the question about the rate law is so the rate is dependent on both the substrate and the nucleophile. So if I change the concentration of either one of those, it's going to change the rate. And that's a consequence of this being bimolecular. So the rate So it's depending on the nucleophile and the substrate. And that's because we call this is a biomolecular and it's concerted. So, right. So let's go back up to, so the fact that it's bimolecular and concerted, that kind of informs us about the rate law, why it's a two-term rate law. That's the whole premise behind saying that it's bimolecular. If we go back up to here, we talked about the other day how in the substitution step, the nucleophile is actually coming in at the same time the leaving group is leaving. So that's why we call it concerted. So the nucleophile, as it attacks, the leaving group is leaving at the same time, and the rate is going to be dependent on both of those. All right. Any questions about this so far? So if you had to only, there's another part on this sheet. Scroll to right here. So this is what the actual transition state looks like. Right. So your nucleophile is here, your electrophile is here, and the incoming nucleophile and the departing leaving group, all of that's happening simultaneously. So for SN2 mechanism, the nucleophile is coming in at the same time that the leaving group is leaving. All right. So let's go to, let me switch gears and we're going to do the E2. Let's talk about that. So let me, actually, I'm going to cut this out so we can have room to talk about it. So what is the, just to see where you are, where your head is, what's the 2 mean in E2?
Bimolecular.
Bimolecular. So it's gonna have similar characteristics to the SN2, and some of the same things that facilitate the SN2 also facilitate the E2. So let me paste this here. Right. So the E2 elimination, one of the things that has to be present, and this is common for eliminations, is that you have to have a base. Right. So here you can see the NH2 anion is going to act as your base. Normally, when you see that, it'll be in connection with something, some other, excuse me, cation like sodium or potassium or something like that. So here you have NH2, and then here you have KOH. Normally, your typical basis for E2 elimination, obviously KOH, sodium amide, but you can also have something like potassium terbutoxide. Sorry about that. All right, so potassium terbutoxide is an excellent base. Sometimes you'll see that written as KO. TBU. Let me fix that K. Right, so the terbutyl part is here. The O is here. Right, and obviously the potassium is the K. So sometimes you'll see that written like that. Another really good base is, make sure I got enough carbons. It's actually an alkyl lithium, N-butyllithium. Sometimes you'll see this written as N-B-U-L-I. Right, the bu is the butyl, the 4-carbon chain that's here. And then the lithium obviously is the metal. right? We've seen these types of organolithiums before, but again, we don't use these for coupling because they're just too basic. And tert-butyllithium is another base that can be used as well. So it's like this is actually a really good base also. All right, so these are you need a strong base to do E2. Simply because the base is what facilitates the proton transfer that leads to the ejection of your leaving group. All right, so because we'll put the products in later. So you need a strong base. This actually works better with tertiary carbons. Right, tertiary or secondary. Primary is not so much, but tertiary or secondary carbons, it works better for those because these give you more substituted alkenes. 1 second. Right, so tertiary carbons and secondary carbons produce more substituted alkenes, which are also more stable. If you notice right here, it says it follows Zepf's rule. We're going to talk about that in a second when we look at some of the reactions, and we're going to talk about the transition state and the rate law. What do you think the rate law is for a E2? If we're comparing this with an SN2 and we're saying it follows a similar, it's bimolecular, saying that it's bimolecular and it's concerted. What do you think the rate law is for E2?
Would it be dependent on the substrate and the nucleophile too?
Well, in this case, it's the base, right?
Oh, the base.
Yeah. But you're right. The rate is K times the substrate times the base. So just like for SN2, when we think about what can help to speed the rate of that reaction up, for SN2, better nucleophiles are going to speed it up. Better leaving groups are going to speed it up, right? Because the nucleophile coming in and the leaving group leaving both have an effect on the rate. So with the E2, better bases increase the rate of reaction. Right, and for your substrate, right, a good leaving group is going to increase the rate. So better bases, good leaving groups, both of those will increase the rate. Let's talk about the solvent for a second, and then we're going to actually go through the arrows and the mechanism for the E2. What do you think about the solvent? What is dichloromethane? Is that protic or aprotic? Based on the list that's in this handout. It's aprotic. Right? That's very important.
I have a question.
Go ahead.
When you wrote down better bases for the rate, are you saying like the stronger the base is?
Yes.
Okay.
So the stronger your base is, the more the rate is going to be increased, because a stronger base can do proton transfer with the substrate faster than a weaker base would.
Okay.
So let me put that in. That's a good question. Great question. All right, so stronger bases increase the rate. Good leaving groups increase the rate. Aprotic solvent. Why is it important? Why do you think it's important to have an aprotic solvent? What if you do this in water? What do you think is going to happen? All right, what do you think happens when I put a strong base in the presence of a proton source or something that's acidic? What do you think is going to happen?
Is it gonna do like photon transfer?
That's it. The solvent is going to be competing with the substrate to do proton transfer. Excuse me. Solvent and substrate. All right. So an aprotic solvent is going to prevent that. So you don't have to worry about your solvent and your substrate competing with one another to do proton transfer. So let me show you, let's take the top example and let me just use that to discuss the mechanism as well as give you an idea of about the transition state. And then we'll do the bottom example to illustrate Zatzel's rule. And I'll send you, that might not be a good idea. I'll send it and then you can just watch it at some point this weekend, but I'll send you more videos dealing with E2 and E1 so you can go back through the information about the E2. But let's take the top example. So I'm going to take this example plus NH2, and I'm gonna let me just put the product in. This is in dichloromethane, right? And it's going to give me this as a product, and then we're going to talk about how. Remember, elimination always results in the formation of a pi bond, right? Now let me put the CH3s in here. So here, let me color code one of them. Right, so that's my product plus that. All right, and we said that this is concerted, and we said that it's an elimination. And so what happens is here at this point, your deprotonation or your proton transfer between the base and the substrate happens here. All right, so the base is coming in here. All right, this is negative. So this is giving a pair of electrons to this proton, right? It's pulling that proton off. And then at the same time, the pair of electrons here between carbon and hydrogen are going here to form your pi bond. All right, so there's a forming pi bond here. And then I'm also at the same time breaking the bond between, right, I forgot to put that up here too. I'll just put Br minus, because bromine is normally, whatever your leaving group is going to end up with the counter ion from your base. Right, so let's say that this is sodium amide. All right, so that sodium is going to end up here with bromine in a like that. All right, so now when we look down here, this is the basic mechanism for E2. The base comes in and does proton transfer. right? Your CH bond, the CH bond is those electrons are being used to form your pi bond. Right? And then the leaving group is leaving at the same time. All right. Question. Any questions about this so far?
I have a question.
Go ahead.
So the base attacks so this all happens at the same time.
Yes, it's all simultaneous.
Okay.
Right. So these protons right here, I forgot to mention that. Let me talk about that now. So these hydrogens on the carbon that are next door to where the leaving group is, these are what we call alpha protons. Right. So those are going to be adjacent to the leaving group site. And those are the only protons that can come off. And there's a reason for that. If you notice here, the proton that I picked is facing downward to where the bromine is. That's on purpose, right? So the alpha, let's talk about that for a second. I can shrink that. Hold up. Make a little room on the side. Right, so those alpha protons and the leaving group have to be opposite to one another. So if I put this in a Newman projection, do y'all remember those from part one? Newman projection kind of look like this. With I'll put the bromine on the back. All right. Yep. Do y'all remember these from part one?
Yes.
Vaguely.
Yes.
All right. So whenever elimination happens, E2 elimination, right? That Newman, okay, so let me back up. This is the alpha proton. This is my leaving group. So when an E2 elimination happens, the alpha proton and the leaving group have to be on opposite sides to one another. It's all based on how the electrons are being donated from the CH bond to make that pi bond. So, and I don't want to get too deep in the weeds with that. But this is what we call anti-periplanar geometry. Right, so that's the alignment of the alpha proton and the leaving group have to be in this geometry in order for E2 elimination to occur. It's really a function of how the orbitals overlap, and the CH bond has to overlap with the CBr bond in a specific way so that those electrons can be donated to kick out the leaving group. All right. Any questions so far? Right. All right. So that's the kind of nuts and bolts behind the E2 elimination. It is, again, you have to have a base, you have to have a good leaving group, And the elimination part is always going to result in the formation of a pi bond. And when I say pi bond, that can be a pi bond to make a double bond, or a second pi bond if you have a double bond and you're eliminating to make a triple bond. I don't just want to say double bond because it can be a double or a triple depending on what the substrate is. All right, but let's look at the second example, and we're going to use that to talk about a couple of other things. And well, before we do that, let me give you an idea of what the transition state for this looks like. All right, so I'm just going to copy this because the transition state is just theoretical, and it's just let me put another. I'll add another page. All right, so this is going to be the so with in the transition state, what is the transition state? What do you know about that from organic one? What can you remember about it?
Well, I remember it's the stage at like in between the reactants and product.
Say the last part again. Your mic kind of went out on me.
Like the point in between the reactants and like the product.
The products, okay. The highest point on the energy diagram. Also, what's happening in the transition state? That's the question I'm trying to get at. Like if you're at that point, what's happening in that molecule in the transition state? Aren't you at a point of like bond breaking and bond making?
Yes.
Some of the bonds are partially broken, some are partially formed. Is that right?
Yes.
Right. So here with the proton transfer part, let me switch my pen so I don't have to have crappy looking lines. There's a partially formed bond between the N and H. There is a partially broken bond here between the C and H. All right. There's also a partially formed pi bond. So I'm gonna put that in here in pink because that's where the electrons are coming from. And then there's a partially broken bond to the leaving group. So those dotted lines mean that the bond is either partially broken or partially formed. Right? So this is partially formed. This is partially broken. Right, this is the pi bond is partially formed. And this is partially broken. All right. And so with that being said, if we think about the overall, like the charge on this transition state, you know, this is negative. So this is coming in as partially negative, and the leaving group leaving is partially negative also. I put partially positive, my bad. Right, so the overall charge on your transition state is negative. This is why the solvent is important. Like it's a polar solvent. A polar solvent is going to help stabilize that. So polar aprotic solvents help to stabilize the transition state. Just going to abbreviate that. All right. Let's look at the next. We got time. Yeah, let's look at the next example. I'm gonna copy it and bring it down, and we'll go through because this is a great example to talk about Zayt's rule. Any questions about what we just did or what we just talked about? Let me get all that on the screen. All right. Let's go to the next example, the next E2 example. Let me just. So we got a couple of things that we can kind of pull out of this example to help us. And so let's first of all, when you're thinking about elimination, you want to identify your base. You also want to identify your substrate. And we see the solvent is DCM. That's no problem. So we know that KOH is the base, right? We know that this is the substrate. This is my leaving group. So once I identify the leaving group, and how do I know that that's the leaving group? Like, what's the clue that I look for to identify my leaving group? Right. What I'm looking.
Secondary carbon.
Okay, it's on a secondary carbon. That's true. But there's another thing that I'm looking for too, and it's the polarity, like the polarity of the bond. Remember, the leaving group is always going to be your most polarized bond in that molecule. So that carbon iodine bond is polarized towards iodine, right? None of the other bonds are polarized like that. So that's a good clue, a good indicator as to which atom in that molecule is my leaving group, right? So this is my substrate, that's my leaving group. What I need to do now is figure out where the alpha positions are. So where would they be in this case? It's not here, right? The alpha position is never on the same carbon with the leaving group. So it's not there. They have to be on the sites that are adjacent to the leaving group. So where are those sites in this molecule?
And one carbon to the left,
So here?
carbon to the right.
Yes, absolutely. So now these are my alpha sites. So I'm gonna make these different colors. And I'll make the other proton some other color. So this is alpha. And this is also alpha over here. So I got two alpha sites, which means that I'm going to get two products. All right, let me put that in here. So the number of products is equivalent to the number of alpha sites. So I've got two alpha sites. That's two places where this thing can do proton transfer. That's two elimination products. So let me first put the products in, and then we're going to discuss how they happen. And then we'll discuss which one is going to be major and which one is going to be minor. Because if you got two sites, then that means that you're going to have competition. And anytime you have competition, that means you're going to have a product distribution between two products. All right. So let me put the two products in over here. And just copy that. All right, so one product is going to be with the double bond here. I had that in red. And then the other product is going to be with the double bond here. Are y'all following that so far?
Well, Can you kind of explain?
Oh yeah, we're gonna go through it.
Okay.
All right. So let's look at it. We know that it's concerted. We already know what the rate law is. It's a second order rate law because it's two terms. But let's look at it. So let me take this here. I'm just going to copy it. Well, no, I'd rather, never mind. Let me just redraw it. Stop being lazy, Russell. All right, so we're going to look at that side first. So here's my leaving group, iodine, and then I'm going to put in my two red alpha protons, right? And KOH is the base. So that is kind of just hanging out here. That's negative. Potassium is positive. It's a salt. Right, so what happens, this is coming here. It's going to attack one of these protons. Both are equivalent, so it doesn't matter which one it attacks, as long as it's anti-periplanar relative to the leaving group. It doesn't matter. So we're going to do this. This pair of electrons is coming here. And then I'm going to kick off iodine, which is, let me put some electrons on that. Right. So when that happens, I get this as a product. I'm just going to steal it from up here. Is that right? Is that the right location for the double bond?
Yes.
And then I get as side products, Ki, because the potassium is just going to form a salt with iodine, because iodine leaves, let me show you, as a negatively charged ion with 4 lone pairs. So I get that plus water. All right, does everybody see where the water came from? The OH, the proton transfer, so now it becomes H2O. And it's the potassium that was with KOH. Let me actually make that a different color, so this might make this a little more clear. I'll make it blue. All right. So over here, this is like so. All right, so the OH pulls off that proton and becomes water. Potassium ends up with iodine as a salt, and then I get my double bond. All of that, the Ki and the water, that's just crap. We don't care anything about that. All right. Any questions so far? Right. So the competing process is when the other alpha site so when you have competitive processes, that means you're going to get a ratio of products. All right, so you're going to have a product distribution. Which means that you're going to have something that's major and a minor product. We talked about this when we talked about allylic bromination, where you have these all these competing allylic sites. So you get all these products, and some of them form faster than others, but some are more stable than others, so on and so forth. Right, so the competitive process is going to be on the other side. Let me just steal this. So crap. Right, that's here. All right, so we get another mole of KOH that's going to do proton transfer. I might as well leave it the same color. All right, so that's coming here like so. And then this is coming here. And then I'm going to lose my leaving group. Exact same mechanism, exact same arrows, exact same everything. Right, so on the other side of this, I'm going to get, I'll just steal it because it's the same stuff. I'm going to get KI, right? I'm going to get water. And I'm going to get that second alkene, which looks like this. Anybody disagree with that? All of this is formed. Yes or no?
Yes.
So with that competing process, again, you open the door for product distribution, ratio of products, major product, minor product. For E2 elimination, if it's following Zaitsel's rule, then it follows that the more substituted alkene is the major product. All right, so for Zaitsel's rule, I'm just gonna really like boil this down to the nuts and bolts. So the more substituted alkene is the favorite product. So it's based on the stability of the alkene. All right, so if let me show you the substitution patterns, and then that'll be it. We'll stop and let y'all enjoy your weekend. All right, so remember in part one, when we talked about alkenes and stability, and alkene can be unsubstituted, so that's here, with no carbons, just all hydrogens. And then it can be mono substituted, where it has one group, one carbon attached. It can be di-substituted. Tri-substituted. You can see the pattern. I'm just adding more carbons in. Or it can be tetra-substituted, which is the most substituted of all the alkenes. So this is unsub, monosub, di, tri, tetra. Right, so the tetra-substituted is the most stable. Right, there's a reason for that. If you think about the think about like how when we talked about carbocation stability, right? It follows a similar trend. So your alkene carbons are sp2. Right, so they are more electronegative than an sp3 carbon because of the percent S character. Y'all remember that from part one? We talked about percent S character. How a sp2 hybridized is more electronegative than a sp3 because it's 33% S, and a sp is more electronegative than a sp. 2 because it's 50% S. So
Yes.
all of these carbon bonds are donating here. Right, so you got these little micro dipoles here. So the more carbon bonds you have around those sp2 carbons, the more stable the alkene is. So I'll write that here. Right, there's a term we use for that. It's called hyperconjugation. We learned that in part 1 when we talked about carbocations, right? So when we go back up to here, we can see that this is a tri-substituted double bond. It's got 3 carbons attached to it. This is di-substituted. It's got 2 carbons attached to it. And so the tri-substituted alkene is going to be more stable, right? So that's going to be your major product. So that's tri-substituted. And this is di-substituted. So that makes that tri-substituted alkene the major product when it follows Zaitsel's rule. All right. Any questions? Any questions? We got to stop here because we over time.
I have a question.
Go ahead.
When doing the elimination to the alpha carbons, if you have 2 out, like for in the problem, there were 2 alpha carbons on it.
Yep.
You do it to each one or just one?
No, just one. They're both equivalent. You can
Okay.
do it to either or. You can pick either one of them because they're both in the same position. Good question. Anything else? All right, we got to stop here. Let me stop recording too.